Hello, students. Let's take a look at the next thing in our chapter. We already have discussed phase changes where we might go from a solid to a liquid or a liquid to a gas. We've discussed those type of properties of matter, whether they're compressible or not compressible. What we're going to look at today is we're going to look at changes in matter. So we have to be able to distinguish between what would be a physical and a chemical property. We're going to need to be able to classify a change, whether that change is going to be a physical or a chemical change. Uh, the lab that we're going to do coming up here, you're going to have to be able to identify some indicators that tell you for sure that you have a chemical change occurring. And then one item that we've already discussed, we went over this with the kinetic molecular theory, where we talked about anytime that you have a change of matter, there's always going to be some sort of energy that's going to be gained or lost in the process. So we might touch on that again in future lessons. And I hope that doesn't get that. Let's take a peek at the definition for what physical properties would actually be. We're describing the physical characteristics, but we are not going to describe how the substance behaves chemically. So I have a couple of examples down underneath the definition. You have a piece of tinfoil. Well, what can you do with a piece of tinfoil? It's the same thing that you can do with a piece of metal. You can pound that metal into different shapes. Now, if we are able to pound and beat on a piece of metal until we can shape it into what we want, if we're blacksmiths, let's say, we would describe that characteristic, that property, as being malleable. All right, so malleable means that you're able to uh, shape those metals or those objects into different forms. So our tinfoil, it might be a big block, and then you pound it out into thin sheets. Your steel, you heat it up in the oven, and then you hit it on an anvil with a hammer, and you form yourself a butcher knife. All right, the next thing, if we're looking at the next item to the right, you have some copper wire. All right, now that copper wire, it just doesn't come in nature in a form like that. What we have to do is we have to draw it out into an actual long piece of wire, and this is called ductility. Ductility. All right, now ductility, we use a press and we forge that material by pressing it through a die. And as we are pulling that material, it will elongate the copper into those thin wires. We have our next one to the right, a physical property. We're looking at boiling point. All right, now I don't have a picture up here, but we could say melting point also. All right, so those two are examples of a physical property. We don't have to chemically change the substance. When you're boiling water, it's H2O. And when it's in the gaseous form in steam, it's H2O. So you're not altering the chemical makeup of it whatsoever. All right, we go over to the next thing. We have what might be some syrup, or could be like Karo syrup. Karo syrup is really, really thick, and the term that we're looking for is viscous. Viscosity. Let's put down viscosity. All right, then I know I'm spelling it correctly. All right, so If we're looking at the viscosity, we're looking at the resistance to flowing. Now, where you might see these terms come up would be with oils. With oils, there's different viscosities of oils that are to be used in your cars at different temperatures, let's say. If you put in a higher viscosity oil into your cars in the wintertime, it may not be very good for your car. So you'd put a thinner viscosity. You have to follow, obviously, the guidelines set forth by the manufacturer, but you definitely wouldn't want to use a very, very viscous, sluggish material in your cars in the wintertime. It just wouldn't be good. It wouldn't lubricate the parts well enough. All right. And then we have the last example. There's more examples in this, but these are just some to give you an idea of what we're talking about. We have solubility. Solubility is an example of a physical property because right here you have a solute. A solute is a solid particle. Well, it doesn't have to be a solid particle. In this case, it's a solid particle that's going to be dissolved in a solvent. So we will do a lab on this a little bit later, and this is a really neat one where we take potassium nitrate and we find out what its solubility would be in water. But coming back to our physical properties, let's say that you have some sugar that you're going to dissolve in a universal solvent, water. Now, the sugar, when you pour it into the water, it no longer looks like sugar. It dissolves in the water. All right, but does that mean that the sugar has chemically altered? Can you still taste the sugar? Sure you can. You can still taste the sugar. If you let the water evaporate, will the sugar be there? Sure. So that is an example of solubility being a physical property. We didn't have any changes there. Let's go to chemical properties now. Chemical properties are a little different. When we're looking at chemical properties, my little symbols here, I know that a couple of them look the same, but we're going to describe them a little bit differently, and you're going to want to know what these are, okay? So chemical properties are properties of a substance that describe how that substance's chemical composition will change given a specific set of conditions. All right, now, how I like to describe chemical properties is they're things that you can only observe while a reaction is taking place, right? So in our first one on the left-hand side, this is flammability. Flammability, you're not going to see flammability of a piece of paper or of gasoline unless there's a fire taking place. You can't observe flammability unless it is actually happening. If you look at the next one, you have radioactivity. All right, radioactivity, if we're looking at the damage that it would cause, well, you're not going to observe radioactivity until it is altering the cellular makeup of whatever it might be exposed to. We have the next one. This one may not be as familiar with you. This is what we would refer to as an oxidizer. All right, an oxidizer is an element or a material that's going to strip away electrons. All right, now a real good example of this, a very, very strong oxidizer would be any of the halogens on your periodic table. So you have your fluorine, you have your chlorine, you have iodine, all of those elements on the periodic table, they all have 7 valence electrons. All right, now, in order for those elements to be chemically stable, they need to gain 1 extra electron. So when they gain that 1 extra electron, they are taking that electron from something else. All right. We have our next one. This one would be what we would term corrosive. And we never want this to happen to you in the classroom. Corrosive is if we have a chemical material. Let's take some sodium hydroxide, for example. If you have some sodium hydroxide and you get that strong base on your skin's going to feel real slippery. All right. Now you might think, oh, that's kind of neat. It feels like there's slime on my fingers. No, that's not really all that good. okay? You want to use some cold water to really wash that off until your fingers don't feel slimy anymore, because it is damaging to your skin. If we go on the opposite side of this, if you go on the opposite side, and let's say that you have some hydrochloric acid that you actually accidentally get it onto your skin, this isn't going to feel slimy. What it's going to feel like is like you have little needles poking at you. All right. That's not a cool thing. You don't want that to happen either. So again, do we use warm water or cold water? You want to use cold water in order to get those corrosive materials off you. But again, let's just say that for our purposes, we're going to be very careful in our labs, and that's never going to happen. We'll go to the next item. We have combustible. All right, combustible. You have a material, it's going to ignite. We're going to have carbon dioxide that's given off, smoke that's given off. So you have a piece of wood, or you have, let's say, gasoline. It is combustible. All right. And then we have our last one. This is the one that everybody thinks of when you think of science class, you think, or chemistry class, you think of explosive. All right. Explosive. We put, let's say, one example of this, if we put into some water some sodium metal. All right. Sodium metal, it's an alkali metal, very left-hand side of our periodic table. If you put it into some water, what's going to happen is it is going to react very, very violently with that water. Okay. That sodium is going to combine with the water, forming sodium hydroxide, and I just ran out of space here, and it's going to free off hydrogen gas. All right. Now we're not going to worry about balancing this yet, because we're not at that step in the class. But in the process of us forming this sodium hydroxide and this hydrogen gas, there's one extra thing that's added on to this. You also get a lot of energy with it, a lot of heat energy. If you have heat energy and hydrogen gas, what do you get? Boom. You get an explosion. All right. We'll do an example of that in the class, where I have a couple of our members of the alkali family that we'll throw into some water, and we'll see what happens. But we have to use Mr. Arnold's fume hood for that. So we'll have to talk with him and organize that. Let's move on here. Now that we have some idea of what physical and chemical changes are, properties are, let's take a look at what the changes might be. So I mentioned the first one before. When we're talking about changes in a substance, let's define changes in a substance that do not involve a change in the identity or chemical makeup of it. So I mentioned this one earlier. I said that we would take some sugar and we put it into some water, or if you have salt, you put it in the water. That process of you doing this, you putting it into here, is called solubility. Oops, there we go. Now I spelled it right. We have solubility. Now, solubility, I said a solid into a liquid, but it doesn't have to be a solid into a liquid. It could be one gas into another gas. It could be a gas into a liquid, such as your pop. If you have carbon dioxide and you put it into that liquid, now you have a mixture. All right. So that carbon dioxide is soluble into the syrupy goodness that you guys would call your pop. If we look at the bottom here, if we have a change that is a physical change here, you have some folding that's occurring. You have some gluing that's occurring, but the paper is still paper. You might have cut it in half. You might have ripped it into little pieces and stuck it onto a frame, but it's still paper. It's not changing the chemical makeup of it. Up at the top, we discussed this one. If you have a phase change here, you have the melting of ice. And if you recall, in order for you to have ice that's going to melt, you have to use that value, that heat of vaporization. Oh, hold on. I'm sorry. I was thinking of steam. We want the heat of fusion. Don't want that confusion. All right. So that heat of fusion, you have to have 80 calories extra per gram in order to change the physical state from a solid to a liquid. All right, and then we have the last example down here. Do you remember what we said this would be? If you have a solid and you're going to pound it into a specific shape, is that ductility or is that malleability? Well, in this case, since we're hammering it into a specific, like a thin sheet, let's say, this would be malleability. All right, so malleability would be that example. So all of these, we're not creating anything new. We are altering the look of it, we're altering the shape of it, but we're not altering the chemical makeup. And something I want to point out before I move on is every single phase change that we're talking about. I mentioned that we had here the ice that's melting, that is a physical change. If we have the water and it's changing into a steam, that's still an example of a physical change. Nothing new is being created. But if we move on and we're going to go to a chemical change now, a chemical change is a change in a substance that involves a change in the identity or chemical makeup of the substance. So what we can say here is something new is formed. If you say something new is formed, you don't have the same thing anymore, so that's not a physical change, that's a chemical change. So all chemical changes are going to be accompanied by a physical change. All right, so let's use the sugar as an example. If you have sugar, we know that when we put it into water, you get that dissociation occurring. You have the sugar, it's going to be dissolved into the water, but you can still taste the sugar. All right, but if we take sugar and we change it into an alcoholic beverage, you're not tasting. Well, hopefully none of you guys have ever done this. We don't want you guys to. All right, but if we were to taste that, we would no longer taste the sugar. All right, because during the process of fermentation, that sugar is going to be chemically altered. All right, so it's no longer going to be sugar. It's not in the same form. It's not like you can have that alcoholic beverage evaporate away and you have sugar at the bottom. It's not going to happen like that. All right, if we have wood, this is a common one. If you have wood, a chemical change that's going to occur here, you have some combustion. All right, so combustion would be an example of one. Down at the bottom, if you have a nail, and it's going to form some rust on the iron nail, that would be iron oxide. So this is called oxidation. You have oxidation. And then the last one up top here, this is not us forming a steam, okay? In this process, we're taking water and we're separating that water into hydrogen and oxygen. Now, if we separate that hydrogen and oxygen, this is called electrolysis. I'm having trouble spelling today. Electrolysis. So that's going to be separating the hydrogen and the oxygen. Now, if we're looking at chemical differences here, all right, we know that the sugar doesn't taste like sugar anymore when it was changed into alcohol. We know that after you burn the wood, you're not going to be able to use it in construction anymore. A rusty nail is not going to have the same rigidity as what a nail would be if it didn't have rust on it. Rust weakens it, and then it'll make it a little more brittle. And then if you're looking at electrolysis, hydrogen and oxygen, hydrogen is combustible, oxygen supports combustion. So you've got like a fire working here, right? But on the beginning portion of that, the water puts out fire. So definitely you have a change in our properties. Okay, so just to kind of emphasize this, If you are looking at physical changes and you're trying to identify if it's a physical or a chemical change, you have to be very careful about your indicators. See, color change is an indicator that you have had a chemical change occurring, but it's not the best indicator. See, in this example right here, we have potassium chromate. If you take potassium chromate and heat it up, it's going to change color. But then when you let it cool off, it goes back to the original color. So just because it changed color doesn't mean that it has chemically altered the material. The same thing can be said about your stovetop. If you have the iron heating elements, it glows red. Just because the color change occurred doesn't mean that your iron heating element is going through a chemical change. Now, on the other side, if we're looking at a chemical change, what is a good identifier? What is the best identifier that you had of a chemical change occurring is if we have, for example, this ammonium dichromate. Ammonium dichromate, once you heat that up and it starts to react, it definitively changes into a new substance. And you can see this orange powder right here, but then over here, you have this, I know the picture isn't great, but it's like a greenish colored material afterwards. That ammonium dichromate, it's not the same thing anymore. And I won't do this one in the class because this stuff right here, it's not good for you to breathe in. It would be very bad for you to breathe in. So that chromium dust that comes off of that, we don't want to be around that stuff. But that's a good example of it, okay? So this is an example of that ammonium dichromate and potassium perchlorate mixed up together. All right, in this case, what I'll do is when I edit this, I'm going to throw the video in here so that you can actually see it. What would be some good indicators that this is an example of a physical or chemical change? After the video that you watch, you determine what those indicators would be. I'll cut that one out. So what would be indicators that ammonium dichromate was actually undergoing a chemical change? Well, in our examples, and these are the things that you're going to have to know for the lab, because you're going to have to identify if chemical changes are actually occurring when you mix aqueous ionic solutions together. So a real easy one is if you see or feel heat being released, that's a pretty darn good indicator that a chemical reaction has occurred. Remember, anytime that you have chemical reactions, you're either going to have energy that's going to be absorbed or energy that's going to be given off. In that example, or even if you light up the Bunsen burners and natural gas ignites, you get light that's produced. If light's produced, pretty good indicator that you had a chemical reaction that has occurred. If you have the production of gas, so when we put the, at my example that I said with the sodium and we add the water to it, what do we get? We get that sodium hydroxide and hydrogen gas from that. So this would be a gas that's going to be produced when we mixed a metal and a liquid together. But whatever you do, don't get boiling of water confused with production of gas. That is not producing a gas, okay? This one is going to be our main focus for our lab, that aqueous ionic solution lab. It's where we're going to identify the formation of a precipitate. Now, precipitate, when we mix two solutions together in the lab, a precipitate is going to be a solid material that forms as a result of those two liquids being mixed together. All right, and I'm not going to elaborate on that right now because in the pre-lab, I show you what this actually is. All right. We go to another change. If you have a change in the chemical and physical properties, like that rusty nail, it's no longer as strong as what that rusty nail is no longer as strong as what that nail was before it had rust on it. It became more brittle. right? We come over here. This, yes, color change is an indicator, but don't solely base your decision, whether it's physical or chemical change, based on the color, because that can be kind of deceiving. If you have electrical current, sure, that's going to be an indicator. Change in volume, not a great indicator, okay? Because if you're looking at ice, its volume changes. It becomes less dense when water in the liquid state changes to that water in the solid state, ice. So volume change can be a good indicator, but it's not the best. All right, what you should never, ever, ever do in here, don't ever do it in here, okay? Bad stuff. Don't ever taste, or if you smell, you can waft it towards you. You wave your hand over top of the material. But if there's a change in the taste or there's a change in the smell of something, then that's a pretty good indicator that we've had an alteration of the chemical composition, right? But taste and smell, those would be physical properties, and if those physical properties change, then that would be a chemical reaction that must have occurred. And then if we alter the physical properties, remember, melting point and boiling points, those are physical properties. And if you're going to alter those, if you change the melting points and boiling points, then you probably have had a chemical reaction that has occurred that is a result of those change in physical properties. Remember that anytime that you have a chemical reaction, drop my pen. Whenever you have a chemical reaction that's going to occur, you're always going to have some energy transfer. All right. So if we have a release of heat energy, remember that Q equals Cm delta T. If we're trying to figure out what that value is. In this case, since we're losing energy, we're releasing heat energy, this would be termed an exothermic process. All right. Our Q would be a negative value. If you are absorbing heat energy, the Q, remember, that's just talking about energy, right? Cm delta T. And if we are absorbing energy, this is what we'd refer to as an endothermic process. And in this case, since we are gaining heat energy, we'd say that that is a positive value. Energy is going into it. So the easy way that I remember these is if energy is leaving, it's exiting. Okay, EX, exiting, exothermic. And if energy is going into, we have endo, exo. All right, so remember those two terms. During these chemical reactions, we're going to start out with reactants. Right, now the reactants are the things that are going to be combined together. All right, so changes occur as a result of changes in the chemical energy, and the changes in the chemical energy might be an increase in its potential energy or a decrease. So let's get to an example right here. This is probably the easiest one to start you guys out with in terms of balancing formulas, because this is something that you guys are all familiar with. You know what water is. All right, so water is made up of hydrogen and it's made up of oxygen. Now, before we start, on the periodic table that I'm going to give to you, you're going to find 7 what are called diatomic elements. Diatomic elements. Diatomic elements are elements that will never be found in nature by themselves. You cannot find just a single solitary hydrogen atom by itself. So, whenever we're looking at reactants, the things that are going to be combined together in a reaction, you have to look at that list of diatomics. If it's one of those diatomics, then you have to make sure that it's written as what I just did, that H2. Oxygen is also on that list of diatomics, so we have to say O2. Now, what does this form? Well, if we provide a little bit of energy here, You provide a little spark. You provide a little spark, what are you going to form? You're going to form some water, some H2O. All right, now we all know this, hydrogen and oxygen. We know that over here that these two are the reactants. We know that this over here is our product, okay, because we made it. The arrow represents yields, so we're making that, yielding that. But there's a small problem, and I want to address this right now. All right, now I'm not expecting you guys to be masters of this just yet, but whenever I give you any of these chemical formulas like this, you need to make sure that these go down in your notes. They have to be in there because I'm going to give these to you as examples on your tests or quizzes. And whenever you have chemical reactions occurring, you always have to abide by the law of conservation of matter. You can't create or destroy matter. So if we count up on the left-hand side here, you have 2 hydrogen atoms. On the right-hand side, you have 2 hydrogen atoms. Great, we're following the law of conservation of matter. If we look at oxygen now, I started out with 2 oxygen. Now I just ended up with 1 oxygen. You can't destroy matter like that. So what that says is that in order to make water, we cannot form just one single solitary water molecule because we can't destroy that additional oxygen atom. So what we have to say is that we put a coefficient in the front. All right, this right here, this coefficient, it's a multiplier. Coefficient is a multiplier. All right, it's a multiplier. It's telling me that I have 2 of these guys. So I have H2O, H2O. That's what that 2 in the front means. I have 2 of those. All right, now, if we look at the oxygens, when I have 2 of those, I have 1, 2. 2 oxygen. Now the oxygens are balanced, but let's go back to the hydrogens now. The hydrogens, I have 2, 4 hydrogen. Over here, I only have 2 hydrogen. So what do I have to put in front of this hydrogen in order to have 4 hydrogen atoms? I don't want to put 4 because if I put 4 there, then I'm going to have H2, 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 and I have 8 hydrogens. That's not good. We don't want that. So instead, if I want to have, again, 1, 2 for a total of 4 hydrogen on the product side, I have to put a 2 here. I have 1, 2 hydrogen for a total of 4 hydrogen. That is a balanced chemical formula. So this guy right here, that's the first chemical formula that you guys should have in your notes and balanced for a quiz or a test in the future. All right. What we'll do is we'll end the video right here, and there is going to be a check worksheet that you guys have to work through to make sure that you understand what physical properties are, chemical properties are, physical changes and chemical changes. Pretty easy stuff. But if you have troubles as you work through this, make sure that you ask for some help. Okay? All right. Until later. Until then, see you later. Bye. Until then, take care. All right. That should take care of it. Hopefully that darn thing doesn't make too much noise.